Um, but let's begin our last lecture. Today, we're still doing polar functions. This time we're asking, today, we'll do some integration. We'll be asking, how do we find the area inside of these curves? That's the subject of our study today. So recall first, if you will, a thing you might have learned as early as Algebra 2 or Pre-Calculus 1, maybe even in geometry, that the length of an arc is measured as r theta. In fact, in some senses, that's definitional. It's like the definition of radians, isn't it? Isn't the radian measure of an angle the ratio between the arc length and the radius? Well, it follows that the arc length, then, is r times theta, provided that theta is measured in radians, as usual in calculus. For small theta, the arc length can be approximated by a line. And so we have this picture here. Again, imagine that this is an arc that we're traversing. But notice that when we're in polar coordinates, as we move from one theta value to the next, we don't have, like in Riemann sum style that we're used to, we don't have rectangular regions, do we? We get like triangular slices, don't we? D theta slices that are like wedges instead. Now, if we're actually talking about a theta value and then some other new theta value, then what we're going to get along the edge here is actually a curve. But for very small changes in theta, we're going to assume that this is a line, right? And then if we're interested today in seeking the area inside these curves, then we'd like to ask about the area. And since now that we can think of this as a triangle, we have the area of the triangle formula that you know and love. So what is the area of that triangle? Well, certainly we know the radii, the radius here. It's whatever the function is there, isn't it? Evaluated at theta. We can find the radius, that's cool, we know that. We also just established a second ago that this length here is r d theta, didn't we? Isn't that how you calculate the arc length? Along the curve. Again, imagine this is a very, very small piece of some polar curve. And we're assuming that for very small changes in theta, that the arc length, and that is the arc length along the curve, and this length of this line are the same. So now that we have the height of the triangle and the base of the triangle, so to speak, I think we can calculate the area of that triangle. What will it be then? 1/2 multiplying these things. R squared d theta? Yes? I hope you see where this comes from, because this is something we're going to use now time and time again. Really, to give you the spoiler, we're just going to throw an integral on that, and like that's going to be it, right? Like we're going to just integrate inside these things using this area formula. But it's not just as simple as integrating a polar function. It's not as simple as that. Well, the thing we're going to be integrating and adding up are these triangular areas of these little d theta slivers, right? So here it is in the larger context of some polar curve. So imagine that you're starting, notice again that you're not like sweeping from some vertical line to some other vertical line, A to B, integrating like we normally do. What are we sweeping from in this case, in polar? Well, we're sweeping from some initial angle, alpha is what I'm calling it, to some terminal angle, theta. We're sweeping through those angles and adding up a whole bunch of triangles. And I have them pictured here using my PowerPoint skills. You want to see that again? That was beautiful. Got to get some mileage out of that animation. Okay. You see the feel of this? Obviously, this is blown out of proportion a little bit. These are, in the ideal sense, infinitely small changes. Right? Taking the limit, doing the integral, gives us, though, the exact area inside a given polar curve. So there it is in a box now. It's just the thing I just said would happen. The formula we just derived for the area of one of these slivers, add them up for all theta values under consideration, right? So that's the one, I think that's the one and only thing we're putting in a box well, I don't want to say that. Yeah, I might have something else on lock. But it's really the only piece of technology we're going to use today. The only piece of machinery that we're going to use. Now, we'll just try some problems, and I think you'll see that we're not in the clear, though. There's some tricky situations with polar curves, especially as we think about the area between two polar curves. These things can get a little bit messy. So we do need to be careful, but that is the basic theory. And do you understand it? Let me ask you for questions if you have them. This undergirds everything else we do today, so make sure you understand it clearly. Do you understand the picture here? It's very important, I think, in all of these problems today that you visualize. If you can visualize these, you're going to be golden. So let's do one. Let's actually find the area inside this cardioid. Again, notice here that I have been nice and provide you a picture, but I didn't provide you limits of integration at all. You know, like what we have to be adding up. But using the formula from the previous page that we developed ourselves together, we're doing 1/2 times r squared d theta. And I took the liberty of squaring the 2 and leaving it on the outside. So that can even be pulled out if you like. And if it's not clear, I don't know, you did the warm-up today and did part C. So I think you know that a lemma cardioid is drawn and is mapped out completely from 0 to 2 pi. By the way, obviously any 2 pi distance will work here. You could do from 2 pi to 4 pi if you like, or something. That would be fine too. Feel free to also use your calculator to do this. Obviously, in fact, there'll be some that we can do by hand here. I think that'll be a thing we do. But by and large, again, we may be reaching for the calculator on a lot of these integrals, and that's okay. So emphasis here, as we've been doing in these last couple of units. Emphasis here on you writing down correctly this integral. Not a ton of emphasis here on you working it out. Okay. Yeah. Oh, yeah, and that's kind of a little bit shady of us to do that. It's just the formula we had before, 1/2 from 0 to 2 pi r squared d theta. That's all. Yeah, I should have written it that way to start with. So see on your calculator, please, just see that you also get 6 pi. Just verify that you can actually push the buttons and get that same answer. I'll give you a minute to do that. I just want to make sure, especially, you can do it this way. You don't have to be in polar mode to do this, right? If you want, you could just do it with X's and stuff. It works fine, or whatever your favorite letter is. It is kind of nice if you already have this in your calculator, though. If you graphed it or something, then you can just use R1 from your variables menu as well. So whatever. A couple different ways to do it. Some way or another, get this answer and prove you can actually get this on the calculator. You see how these little slivers are happening? This is from 0 to pi I've pictured so far. I just want to make sure you actually understand what it is we're adding up. Okay? And then the same picture down below, right? When then we keep going past pi, like we're getting these slivers. Right. It was pretty. I know, and I get tired. Okay. Did you get 6 pi? Good. It does leave you wondering, there must be a nice way to do this without the calculator. It comes out to such a nice answer, there's gotta be a way. So I'll leave that as a challenge for you. That is, in fact, though, a little beyond the scope of anything we ask or expect or in this course. So, okay. But I think using some trig identities, you could actually figure that out using some knowledge from your trig background. Did you have a question, someone? I thought I had. You're good. No? Yes, no. Just highlight the word sometimes here. So, so sometimes, if you're calculating the area, you can imagine the situation. Imagine we, I don't know, put a circle inside of a limaçon or something. I don't know, or inside of a you know, limaçon doesn't have an inner loop or something. Yeah, certainly we get slivers here. We get slivers here. We can subtract those two areas. But highlight the word sometimes here. I'll just say this. Well, we'll do one like this. There are cases that are more complicated, but we'll get to one of those in a second. But in this particular case, I think you'll find this to be a good approach. So I have the picture here ready for us, for those who don't really want to think about it. R equals 2, I think, is a picture we all know. The circle of radius 2 centered at the origin. And then this is another cardioid, similar to the one we were just doing a minute ago. We're asked to find the area inside, this is, the wording here is key, inside the circle, but outside the cardioid. So which region am I shading here if I wanted to shade a region? Yeah, how would you describe the shape of that? Like the Batman logo, is that what you're going to say? Yeah, I thought so, okay. So it's like this region in here, right? Do you agree? That's the region we seek the area of. Now, I don't want to just have you take my word for it that this formula applies in this situation. I really want to zoom in on this and like make sure you understand why this makes sense in this situation. In yellow, I'll highlight a sample region here. There's a sliver, a d theta sliver for an example theta from the outer region, yeah? That comes from, let's just be clear, which function got me that yellow value? Go back to the picture, go back to the two equations. Yeah, that's the circle, right? I'll highlight that in yellow. And does this make sense that we can subtract? Oh yeah, I guess so, because if we're sweeping along the inside one, in green, we have this value, yes? And does the difference of these make sense in this situation and we add up all those differences? Yes, yeah, I want to make sure you're clear on that because, again, very shortly, this formula won't apply and I want to make sure you're good on this. When it applies and when it doesn't. Anyway, once we're assured that this applies, then it's easy and you'll hand this to your calculator, right? So, well, I don't know, maybe there's still a hurdle to cross here. What are the limits of integration to? What'd you say, from what to what? Yeah, 0 to pi would work. What else could you do? Taking advantage maybe of the symmetry of the curve. So I get that all in there. There's one more parenthesis missing there. Yeah, you could also go from 0 to pi over 2, and then double it maybe, right? You can always be using the symmetry of these curves. For example, in some of these we might do a rose curve and find one of the areas of interest, in one of the petals, and then multiply it or something. Right? Yeah.
Why wouldn't you be able to go to 2 pi in this situation? What makes this different?
Yeah. So let's just make sure this. When does this picture we drew here apply? It makes sense when we're talking about 0, a theta value of 0. It makes sense all the way to a theta value of pi. But if we do that subtraction later, after pi, then what are we doing? Aren't we taking the area inside the circle, that sliver, and subtracting the area outside? It's starting to become nonsense for us. It would be completely okay, though, to ask, like, what's the region out here? What's the area of that region? But I would do that with a second calculation, just like when there was, like, we were doing area between curves and the top function switched and became the bottom function. That's actually what's happening down here, so you need to be careful. It's completely legitimate for someone to ask you what's the area of this canoe-shaped region. I don't know, is that a good word for it? That would be fine. Huh? Crescent-shaped region, okay. But then you would do the same setup. You might go from pi to 2 pi, and you'd have the two functions switched in the way you subtract there, right? So All right, so someone can tell me what you get there if you like. I don't know off the top of my head. But does anyone? They don't already get it? It's okay if you don't. Well, that's not the important part here. Sometimes this is all I'm giving you. Nothing about this. Sometimes it's. I'll just say this. It's more complicated, right? So let's try. Let's try this region again. I have a picture for us. May not be obvious to you that this is a circle. I'll just tell you that it is. The first one is obviously a circle, a unit circle. The second one is a circle too. Plot some points and figure that out, or you could remember that that's true, or you could think of it as a rose curve with only one petal, or you think of it as a limaçon, a degenerate case of a limaçon too. Something funny about the word degenerate. I'll pretend like it is. Do you see already why this is more complicated and why the previous formula doesn't apply? Let's first shade the region of interest and then try and actually make some slivers that represent the thing we want to calculate here. So what is, I'll highlight in red again, what is the area of interest, the region of interest? Find the area shared by the two circles. So what does that mean? The wording is of course important on these. Yeah, the intersection of the Venn diagram, I like this. This is good. We could like tie in probability or something. That'd be fun. Okay. But yeah, this like football-shaped region here, right? I think we all have that in mind. And then let's again zoom in on this and be really careful with our analysis. Okay. So as we sweep through angles, let's keep in mind that this is the pole, isn't it? And in fact, just to be, let's make it before we even start drawing like sample curves here. Let's actually, I should have done this to start with. Let's actually highlight this one in yellow, this whole curve in yellow, and ask ourselves, what is that? That one, which one's that? I pulled it from this picture, so what was that? That's r equals 1, isn't it? And this is the other one, right? All right, now we're sweeping angles from this point along this curve and seeing what we get, right? So what happens if we start sweeping from 0 and we start making triangles? What are we hitting and what are we not hitting? Notice here that we're only pulling values from this curve, right? So as we draw sample theta values, we're sweeping only along the green curve, aren't we? As we sweep, you can imagine by sweep here, I mean like you're extending a ray out from 0 in the theta direction of your choice and sweeping it along the curve. And for the first part of this curve, it just simply doesn't intersect the yellow curve in the region of interest that we're looking at, right? So I'm going to start by calculating that green sliver. But then when we get to the point where I've stopped, what starts happening? Yeah, the boundary changes. You like this whole sometimes it's more complicated thing? Okay. But now, as we move up here, and in fact for a long time, we get these slivers coming only from the yellow function, right? All the way over to here again, yes? And then we have green again. Now, so one way to do this would be to set up 3 integrals, or what? I mean, the region of interest has been highlighted before us. This is definitely the thing we want to calculate. And that would work. You could separate it into 3 integrals. Or do what? Yeah, how could you get away with only 2 integrals here? Yeah, there's symmetry here, right? So in fact, maybe you could just get away with calculating this part and then doubling it. Or you could calculate this whole piece and one of these and double it and add it, or whatever. Do whatever you like. Just get, in the end, get the geometry right of the situation, right? Okay, good. So I think that's what I'm going to do. I'm going to, take half of this, what theta values, do you already see which theta values we want to consider? We want to consider all triangles here, all triangular slivers from theta equals what to what? Yes, I think it's made clear by my picture here. I want to consider all theta values from 0 to pi over 2, right? Good. So here we go. The area will then be 2 integrals, 1/2, 0 to something, we haven't figured it out yet though, plus 1/2 the integral from something to pi over 2, That's progress. Kind of. What do we need? We still actually do need something, don't we? I don't know if this is on the calculator section or not, but don't we need to know where that point is? What theta value that occurs, where we switch over? So you tell me. When is 1, when does R value 1 equal the R value 2 sine theta? For what theta value? Well, we can find the intersection between curves and polar coordinates as easily as we can in rectangular coordinates. What theta value is that? Yeah, conveniently. 5 or 6. What's the other one? 5, 5, or 6. You notice that there are an infinite number of solutions to this equation, but the one we seek is 5 or 6. Okay, so I don't know whether this happens on a non-calculator section or a calculator section, but be prepared to do this kind of algebraic thinking in order to find that other boundary point if you need it. Okay. All right, that was, I think we've passed the tricky part. We just need to make sure we get the right thing in each of these integrals. The first integral is the green one, so we're doing 1/2 that R value squared 2 sine theta squared d theta. And the second integral is very simply 1, I'll write squared, but you know, d theta. Which, by the way, we expect it to be relatively simple too. In fact, we could do this integral by hand. It's just a portion of a circle, and you could use geometry to figure out the yellow area. Any area in the yellow region you could probably figure out using just geometry. So that second integral is simple for a good reason. But again, I don't know that we have talked about, and we're going to make a point of emphasis, how to do this algebraically, this first integral. So again, feel free to use your calculator. Or, I don't know, maybe we should just like once and for all like tell you how to do it. There's a power reducing formula from trig. Well, okay, let's just use your calculator. It's fine. It'll come out nice though, I'll just promise you that. And again, for the are there any questions about the setup? I don't want to belabor like putting this in the calculator necessarily. I think you can do that. I don't want to make that a huge focus of the lesson. Yeah. Oh yeah, please. Yeah, exactly. Sorry. Good catch. The area will be all of this times 2, and you're right that can eliminate the 1/2 if you like. That would be a convenient algebraic thing to do. Even if you do have a calculator, you might do that just to save your button pushing. Good catch. Multiply that by 2. You see how it can be sometimes more complicated? And I hope you see why drawing a picture just gets you everywhere. Really thinking carefully about which parts of the curve we're hitting, all that is super important, I think. Let's see who at least can get the setup on the last one. I think I have one more example I'd like to share with you, and we'll at least get it point you in the right direction at least.
Wait, why do you have to do this?
Only because we calculated only half of the regional interest. That's all. Does someone have an answer there already? 1 point what? 1.228. She says. Anyone confirm that? Confirmed. Okay, good. All right. I guess we'll trust all these people, all right? No, maybe not. I don't know. All right, we got a rose curve. Do I have a picture of this one? That was nice of me. Okay. Find the area inside the 4-petal rose curve and outside the circle. So what region or regions are we speaking of? Yeah, like the ends of the petals, right? There, 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 there. So is this a nice one? In some sense it is, right? There's some snags along the way. But I think it's very clear that it would make sense for us to do only one of these. In fact, there's actually, and then multiply by 4. You can actually do one other thing if you really wanted to use symmetry, if you really wanted to maximize the symmetry of this picture. And that's to calculate half of one of these petal ends and multiply by 8. You can do whatever. Do what you like. I don't think that doing 1 and multiplying by 4 will be any easier though, any harder though. So let's do that. We'll do 4 times whatever we come up with. So what is the area inside this? On this particular one, can we do the subtraction thing? I think we can this time, yeah? We'll just think carefully about that. Yeah, each one of these, I won't draw it out, But I think that red region can be calculated by making slivers, subtracting the two triangular slivers, and finding the area in between. So I think that will work here. So we got 1/2 times the integral from outside squared minus inside squared d theta. We just need limits of integration, right? That's a pre-calculus problem again. Where do these intersect? Good. This is good. You have to think about your trig, right? What do you get? Yeah, I think it's negative to positive pi over 6, right? You'll get pi over 3 here, plus or minus pi over 3. But then you'll divide by 2, so it'll be plus or minus pi over 6.